Hi. So today I'll be talking about hardware implementations of recurrent neural networks as part of my ECE1385 literature survey. So in this talk I'll discuss what recurrent neural networks, or RNNs, are. I'll talk about a specific type of RNN called a long short-term memory, or LSTM. I'll also discuss what deep RNNs are. And then from there I'll move on to the paper I'll be studying for this presentation, which is an RNN hardware implementation on an FPGA. So I'll start off by discussing what the pseudocode for an RNN looks like, then how that translates to a dependency graph, to a signal flow graph, and finally the implementation that was presented in the paper on the FPGA. I'll also discuss some of the performance comparisons that was done in the work. From there I'll discuss possible future research in this area based on what improvements we could make on that paper. And finally, I'll conclude the talk. So, what are RNNs? RNNs are neural networks that process sequences. So it uses a history of inputs to determine the output. And so there's dependencies on the output, not just on the current input, but on previous inputs as well. So for example, if we look at some of the scenarios that are presented on this slide, we could have a sequence of characters or words in a sentence, and RNN could be trained to figure out what the next character should be based on the previous characters, or what the next word should be based on the context of the sentence or multiple sentences. RNNs aren't just useful for text, they can also be useful for images. For example, if we have a street view of a house number, the neural network could focus its attention on different parts of the image, and based on the sequence of those attention spans, it could generate what the caption, or for example, what the number is in the image. So the basic structure of an RNN really involves a feedback loop. So an RNN uses feedback on a hidden vector sequence, and that vector sequence is h of t. So if we look at the top left of the slide, we have a simple processing element that's really the heart of the RNN, and that's in feedback based on that hidden vector sequence h of t. So the processing element has two inputs, x of t, which is the input vector, as well as h of t minus 1, which is the input, the hidden vector from the previous time step. And the processing element then generates two outputs, the output vector y of t, as well as the hidden vector sequence at the current time step, h of t. So based on this feedback loop around the processing element, we can imagine this loop enrolled over time. So for example, at the first time step, x of 0 is the input, and y of 0 is the output of the processing element. And also the processing element also generates h of 0. At time step 1, h of 0 then becomes the input to the processing element, as well as the next input vector, x of 1, and then it generates the next output vector, y of 1, as well as h of 1. And so this continues, so on and so forth. And so really what's key here is that the hidden vector, h of t, is really sort of the state vector of the RNN. So it's passed along through time, through the multiple iterations of the processing element. So also on this slide, I'm presenting what a processing element is. So really it has two functions. It's equivalent to having a vector matrix multiply based on weight vectors w. And so these weight matrices w. And so these weight matrices are pre-trained based on a learning algorithm that sets the parameters of the recurrent neural network. So once these matrix vector multiplies are done, the processing element also has to apply a hidden layer function, which I call capital H here. So this capital H is just a nonlinear function. At the simplest form, an RNN can assume a tan H, or a hyperbolic tangent function. But the details of the implementation of this hidden layer function, as well as what actually goes inside the processing element, really depends on the type of recurrent neural network we have. So one popular type of recurrent neural network is long short-term memories, or LSTMs. So normal RNNs use a hidden layer function, capital H, which is just the hyperbolic tan function. So I'm showing that as the processing element on the left of the slide. So for that processing element for a normal recurrent neural network, it has some matrix vector multiplies, which goes through a hyperbolic tan function and then produces its outputs. Now the challenge with these RNNs, and what led to the sort of lack of popularity back in the early 90s, was that the training for these RNNs is very difficult, especially for long-term memory dependencies. And so the details of that I won't go into too much in this presentation, but there's a very famous paper by Benjo's group from the University of Montreal who discusses that, and I cite that at the bottom of the slide. But an alternative to get around this issue of training for long-term memory, there was another proposed type of RNN which is called the LSTM, or long short-term memories. And so really these long short-term memories are much easier to train, but they're also much more complicated. So you can see the processing element on the right 2/3 of the slide here. It's much more involved in terms of what the hidden layer function is. But the crucial part I want to point out is what's highlighted in red. So the LSTM adds an additional cell state, CFT. And the CFT is used to combine with the input X of t in such a way that it can remember or forget, so either cause changes or modify the hidden state vector H of t. So in literature, this is usually referred to as a forget cell, which is a feature of the LSTM. And so this forget feature enables the training of these LSTMs to be much simpler. Now, this may look complicated, but from really the key point of this slide is to show that there may be different types of processing elements depending on the variant of RNN. But at the end of the day, the high-level structures of the processing elements is still the same. So what really matters is how the processing elements transfer and communicate data with one another, and how we schedule the data transfers between the elements. So for example, one way we can do that, connect the processing elements together, is in a deep RNN configuration. So a deep RNN is really constructed by layers of multiple RNNs. So for example, if in each horizontal row here I have one RNN, I can have n RNNs stacked together to form an n-layer deep RNN. And so the way a deep RNN works is the output of one RNN layer becomes the input of the adjacent RNN layer on top of it. And so this can really enrich the performance of a recurrent neural network. So for example, the paper I want to discuss for this presentation is using a 2-layer deep RNN for character prediction. So let's just jump right into the paper itself. The paper I'm discussing is titled Recurrent Neural Network, Hardware Implementation on FPGA. And so the authors discuss how an LSTM-based RNN can be mapped to hardware on an FPGA. The FPGA they chose was a fairly small, low-power FPGA, more targeting towards mobile coprocessor type applications. It was a Xilinx Zinc FPGA. And so the RNN they used was to generate 1,000 characters for Shakespeare-like text. So the RNN would generate 1,000 outputs over 1,000 time steps. And those characters would be combined together to look something like what Shakespeare may have written in one of his plays or poems. And so as I said before, this deep RNN uses just 2 layers. They also discuss some performance comparisons with other types of platforms, which I'll get into later in the talk. So first off, before we discuss the implementation on the FPGA, it's useful to understand how we got there. And so to do that, we should understand how the RNN works from an algorithm perspective. So on this slide, I'm showing how both the pseudocode on the left as well as the single assignment language, or SAL, on the right. So on the left, we have the pseudocode for the recurrent neural network. We're showing the computations for both the hidden state vector h of t as well as the output vector y of t. So we can make observations here and convert that pseudocode into the single assignment language on the right. And so I'm showing, for example, h of t, the computation for that. We can expand that both across time and the index of the layers. So time being t and index being n. And so we can do that to make sure that each assignment is only happening once. And we can also make sure that the weight matrices and bias vectors are localized instead of broadcast to make sure this is a locally recursive algorithm. But in any case, for the SAL description on the right, we have a description for both h of t and y of t. And so we can use that to create a dependency graph, which I'm showing on this slide. So crucially, the dependency graph shows that each processing element depends on the RNN layer below it at the same time step, and the time step before it on the same RNN layer. So for example, h of 1 on layer 2 depends on h of 1 at time step 1, as well as h of 2 at time step 0. So I guess the point of the slide is that the SAL was useful in converting to the dependency graph of this 2-layer RNN network. And so what the paper did was it took 1,000 samples, output samples, to generate the 1,000 character text. And so that meant that the output sequence varied from y equals 0 to y equals 999, from time step 0 to 999. And of course, there are weight matrices and bias vectors that propagate here. They would propagate horizontally along each neural network layer. But I'm not showing them here just for brevity and clarity of the figure. So from the dependency graph, we can describe a schedule vector. If we define the axes, for example, as time being on the horizontal axis and n being the index layer being on the vertical axis, we can define a schedule vector, for example, t equals 1, n equals 1. So a diagonal schedule vector. And in doing so, we can define some hyperplanes based on the time steps, which could be useful in scheduling our inputs and outputs. But really, we can also use this to come up with valid projection vectors based on the schedule to find some signal flow graphs that may be useful for implementation. Now, the key point here is that a recurrent neural network is, in theory, infinitely long. It goes infinitely long back in time for its history. And so the time axis for the dependency graph is unbounded in the horizontal axis. And so that has an impact on the on the signal flow graph, or on the projection. If we are to project in such a way, for example, for d2 equals 0, 1, so the projection vector is normal to the time axis, or if we have d3 equals 1, 1, so the projection vector still has some component that's along the t-axis, then that unboundedness in the time axis shows up in our projections as well. So for the top and the diagonal projections, they will also be unbounded in the number of processing elements they need. But for example, if our projection vector is parallel to the time axis, for example d1, which is equal to 1 in the time axis and 0 in the n-axis, then that unboundedness essentially gets collapsed, and so we end up having just 2 processing elements that can schedule and sequence the inputs and outputs as needed. And so this is a useful observation in that now the number of processing elements is bounded. Now we need as many processing elements as the number of neural layers in our RNN, deep RNN. So the signal flow graph that was implemented on the FPGA I'm showing on this slide here. And so interestingly, they used the d equals 0, 1 projection, so the top projection on the previous slide. And so that involves an unbounded number of processing elements. And so the problem there was the FPGA itself was hardware limited, and so they couldn't have an unbounded number of processing elements. They only actually ended up implementing just one processing element, and they had a controller or an FSM that would schedule the data going back and forth from the processing elements. So for example, the controller would take the processing element output stored into external memory, DRAM, and then it would decide whether or not the processing element should compute for the next time step or the next layer. And then it would retrieve those the relevant inputs from the DRAM and then store them and then input them into the processing element. So based on that observation, the final implementation on the FPGA is shown in this slide here. So on the left, we can see really what's the main implementation on the FPGA, the LSTM module. There was one LSTM module for the FPGA that communicated with main memory through direct memory access, or DMA protocol, or IP. There was also an ARM processor that was used to configure the memory and the LSTM module, but that wasn't used for the computation itself. On the right hand of the figure, I'm showing the gate modules and the final stage modules. So these were sub-modules that were used for the LSTM specific operations. So one thing to note here is that this implementation with just one LSTM module consumed 23% of the DSPs on the FPGA, and that was the limiting factor here. So the FPGA was fairly small. The performance comparison I'm showing on this slide here, so the second line in the graph, the LSTM hardware for this work, took about 1.0 seconds of execution time for 1,000 characters. Now the paper does claim that having 8 LSTM modules in parallel would reduce this by a factor of 8 to 0.1 seconds, but they're not clear about the implementation details. But in any case, they do achieve a 21x throughput increase compared to a CPU running on that same FPGA, as well as 2.8x faster speed up than a GPU. But the GPU, I suspect, was limited by memory accesses, and so I'm not sure if this would scale with larger RNNs. So in terms of future research, there's two things I'd like to discuss here. First of all, why was that particular projection vector d equals 0, 1 used, where it resulted in an unbounded number of processing elements? For example, if we use the alternative d equals 1, 0 projection, which I'm showing on this slide here, that would bound the number of processing elements, and we could still schedule inputs and outputs in a systolic way without having to deal with scheduling issues by a controller and external memory. Secondly, is it possible to pipeline the processing element in such a way that we can continue processing while fetching memory? And so, for example, we could propose having 3 pipeline stages where the previous inputs ht-1, ct-1, and x of t are fetched from memory. The processing element executes the computation and then stores them to memory as well while the next inputs are being fetched. And so this may present some speed up increase, assuming that the limiting factor here was the memory accesses and not the processing elements themselves. So just to quickly conclude the talk, RNNs are very powerful and useful tools for processing sequences, especially when the output depends on the current and the previous inputs. Typically in modern RNNs, the long short-term memories, or LSTMs, are used. It's just easier to train, especially for longer histories. One FPGA implementation was shown, and I went through sort of going from the pseudocode to the signal flow graph to finally the implementation on the FPGA itself, as well as some possible speedups based on pipelining or different choices of projection vectors. And so here are some of the references I used in this talk, and that's it for my presentation. Thanks for your attention.